look at the last topic of this chapter, that will be power. Okay. Okay, what is power? Yeah. In the most the simplest way, that power of any optical system like lens or mirror can be defined in a very simple way like this. Power is ability to bend light. The simplest way that can be understood. Okay, a lens or light passes through a lens, its direction changes, it bends, it deviates from its direction, gets reflected from the mirror, it gets deviated. Okay, the more the deviation, more is the power of the lens or the mirror. Okay, now let's look at one example here. Let's say that I have this convex lens. Okay, on this convex lens, parallel beam of light is incident. Okay, parallel beam, it's like this. Here it is. Now, let's say that this is focus. This is focus. Okay, this is the original direction. This is the original direction, and this is the focus. Light rays are going to focus here at this point. Okay, what is the bending? This is F1. Okay, I'm calling it F1. Let's say it is not the first focus. It's just F1. Okay, I'm going to write. Or let me write it as F. That's it. Okay, just in case you get confused. Now this is the deviation. This is delta 1. The light ray gets deviated by this angle delta 1. Now what will happen if this lens has a different focus? Okay, let's say that the focus is smaller, the focal length is smaller, this is f dash. What is the effect on bending? Now the light rays will bend here. Okay. This becomes deviation. This becomes delta dash, delta and delta dash. This becomes delta dash. Now what we see, one thing is very clear. Okay, if focal length decreases, this bending is decreasing. Okay, this bending it increases, and so we say that power increases. Focal length decreases, bending increases, power increases. Okay, the same thing happens with a concave lens also, a diverging lens also. Let's say that I have this diverging lens. There is same relationship. Same relationship. I have this light ray. Let's say that this is my focus. Okay. Now, so the light ray after passing through this lens are going to be deviated like this. Okay, this is the original direction. Okay, this is the original direction. Okay, that's how the light rays are going to diverge after passing through the lens. Okay, what will happen if the focal length is different, if it is smaller? Okay, let's say that this is the focus here, f dash here. Okay, in the first case this is deviation, this is delta. Okay, now if the focal length becomes smaller, okay, in that case the deviation, the divergence will happen from here. Okay, this is the deviation has increased. In both cases, convex or concave, in both cases the divergence has increased. Okay, so focal length decreases, deviation increases, we say that power increases. Now, how do we define? Power is defined as okay, for lens we define power as 1 over F. That's it, 1 over F, just simply the reciprocal. Okay, and for mirror, power is defined as minus of 1 over F. Minus, okay, keep this thing in mind. This is power of lens, power of mirror. Power of lens 1 over focal length of the lens. Power of mirror minus 1 over focal length of the mirror. Okay, in either case, okay, let's see, very interesting thing. If lens is converging, convex converging lens. Focal length is positive. What is power? Power is positive. Okay. Now, a concave mirror. Try to recollect. Try to remember. A concave mirror. What is focal length? Focal length is negative. Concave mirror. Focal length is negative. Okay. What will be power? Power will be positive. A concave mirror is converging. A convex lens is converging. Power for both is positive. Okay, that means power of a converging system, whether it is lens or mirror, is positive. Okay, power of a converging system. Okay, it can be lens or mirror. Lens or mirror is positive. Okay, and power of a diverging system, okay, is negative. Okay, so power of a converging, this is a converging system or this is a converging system. Convex lens, concave mirror, power is going to be positive. Okay, a concave lens and convex mirror, both are diverging. Their focal lengths are negative, power is negative. Okay, now unit of power. Unit of power. Okay, it is of course SI unit. It is 1 over meter. That's it. It is meter minus 1. It is also known as diopter. Diopter D. Okay, so 1 D is equal to 1 per meter. Both are SI system. Okay, both SI, diopter is an SI unit. Okay, this is a power of a lens. Power of a lens 1 over F L, 1 over minus 1 over F L. Now, what if I have more than one lens in contact? Okay, let's see. Power of combination. Okay, power of combination. Power of combination of lenses. Okay, let's say that I have one lens here. First, case 1. Case 1 at separation D. Okay, I have this lens here, another lens here. Okay, separation between them is D. Okay, focal length is F1 and power is P1 for this first lens. Second lens, focal length is F2, power is P2. Okay. Now this is equivalent to a single lens of power focal length F, let's say it's capital F, and this is a capital P, power P. Then what will be power of combination? It is P is equal to P1 plus P2. That's it. Power gets added. Okay, power gets added. The deviation gets added. We did this in reflection as well as refraction. If light ray undergoes successive deviations, then net deviation is going to be simply the summation of all the deviations. Okay. Similarly, power also. Power is nothing but the bending. Power is directly proportional to deviation. More deviation, more power. Directly proportional to deviation. Okay. So as the light ray starts bending successively, net deviation is equal to the summation of all those deviations. That similarly, net power is summation of all those powers. Okay. Okay, here, no, I think this is one mistake here. One mistake. What is this? This is not right. Absolutely not right. Okay. In case of this, at separation, okay, here a different relation exists. This power is equal to P1 plus P2 minus D times P1 P2 minus D. Okay, and then focal length 1 over F is 1 over F1 plus 1 over F2 minus D over F1. This is case 1 where the lenses are at some separation. Okay, case 2. Okay, lenses in contact. Lenses in contact. Okay, so I have this lens here. Both are in contact. I have two thin lenses. Two thin lenses are in contact. So this D becomes 0. Okay. So this is F1 P1. This is F2 P2. This will be equivalent to a single lens of power focal length F power P. Here P is simply equal to P1 plus P2. Okay. The logic remains the same. Deviation gets added, power gets added. That's it. Here there is some influence of D, okay, that we do not have to worry about. Anyway, this relationship is very useful. This is something that we do only this part, that's it. Okay, so if in some exam, some question, if problem is asked like find the image, find the final image. Like we did in the last lecture, we did some problems where we had a combination of lenses and mirrors, and we are required to locate the final image. Okay, how do we do it? We find image successively, first by one system, then by the other system. Okay, we do it in sequence. We chase the light ray. Okay, we never actually use this formula. Okay, this formula has its own danger. Okay, so you just note it down. Okay, so if the question is asked just to find focal length, only find focal length, then I can use this formula. Now, if the question is asked to find the image, then never make use of this formula. Never. It is going to get us becomes very confusing because this whole system is equivalent to this lens, but then what is the position of this lens? I have some object here. When I am writing the object, suppose I got the focal length of this combination. How will I apply the formula? Lens formula 1 over V minus 1 over U, 1 over F. If I ask you to write U, object distance, so you will take your object distance from this lens or this lens. It becomes very confusing. Okay, actually this equivalent lens is somewhere in between here. Not here, somewhere in between here. Okay, it depends on F1, F2 and D. It becomes very complicated. Okay, we almost never use that thing. So what we actually do is, we look at the images one by one. First image from this, then by this. Then we get our answer. Okay, but we can do that here in this case, when both are in contact. Then the equivalent will be here itself. Okay, so the object distance will be same. For this lens, as well as for this lens. Okay, and this is the form that is most useful, and we are going to solve a few problems based on this only. Okay, now let's do a few problems, and then that's it. Okay, it's like this. Or converging and diverging lenses of focal lengths, okay, 20 centimeter and 50 centimeter are placed in contact. Okay, what is power of combination? What is power and focal length of combination? What is power and focal length of combination? Simple problem. We are starting from this. A very simple problem. Okay. So I have this converging lens and then a diverging lens. Both are kept in contact. Okay. The focal length here, f1, is 20 centimeter. Okay. So are you solving it? So pause the video. You have to pause the video and then solve it. Okay. We are now here. And I'm going to discuss it. You should pause the video and then here is how to solve it. Okay. So f1 is 20 centimeter and this f2 here is 50 centimeter. This is converging, this is diverging. Now what is the relation? Power of combination. Power is P1 plus P2 and focal length 1 over f will be equal to 1 over f1 plus 1 over f2. For two lenses in contact. If I have 3 lenses, 4 lenses, 5 lenses, so I just have to add all the powers. Okay, got this idea? Focal length is given. So either I can use this, I can find focal length of combination, and then from there I can find power, or I can find power first, then I can find focal length. Okay, let's do it both way so that you understand, you are not confused. So first let's use this 1 over f is equal to 1 over f1 plus 1 over f2. 1 over f1. f1 is converging length. Converging is 20 and diverging is 30. Converging focal length positive. So plus 20 here plus 1 over minus 50 here. This becomes 100 plus 5 minus 2. Okay. So this focal length becomes 100 over 3 plus 100 over 3 centimeter. What is this? This is focal length of the combination. What will be power? And that is where we make mistake. If I write power is 1 over f, this will be equal to plus 3 over 100 diopter, and this is the biggest mistake I can make. Diopter is an SI unit. I will have to write focal length in SI. That means in meter. Then only I will get my power in diopter. Okay. This is the mistake that you have to avoid. Most common and the most silly mistake. Okay. So what I will do is I will write f is equal to 1 over 3. It is plus 100 over 3 centimeter. It becomes plus 1 over 3 meter. Then I can write power is 1 over f, which becomes plus 3 diopter. Now this is right. So this is the focal length of combination. This is the power of combination. Okay. Let's look at the other way. Okay. F1 is plus 20 centimeter. So plus 20 over 100 meter. Okay. What is power? P1 is 1 over F1. It is going to be equal to, so this becomes plus 1 over 5 meter. This becomes plus 5 diopter. Okay. What is F2? Minus 50 centimeter diverging length. This is a minus 50 over 100 meter minus half meter. So what is power? 1 over F2. This will be minus 2 diopter. Minus 2 diopter. Okay. Now, what is power of combination? P1 plus P2. Okay. So plus 5 plus minus 2. It becomes plus 3 diopter. Same answer that I am getting here. Once I know the power of combination, I know the focal length. Okay. What is focal length? This is 1 over P. This is plus 1 over 3. Now this will be in meter. SI unit. Power diopter is SI unit. Okay. So this becomes plus 100 over 3 centimeter. Same as this. Okay. Got it? Okay, let's do few more problems on combination. Okay, it's like this. Question of plano convex and plano concave lens. A plano convex and a plano concave lenses, each of radius r and refractive indexes mu1 and mu2 respectively are fitted as shown. Okay. Find power and focal length of combination. Okay, it's like this. I have a plano convex lens. Okay, and this I am fitting it with this. Because what do I get? I get actually a structure like this. Do you see? This is R, this also is R, this is mu1 and this is mu2. So two lenses, a plano convex and a plano concave, they are pasted together. From outside it will appear like a rectangular slab. From outside it appears like a rectangular slab, but it will act like a lens, a converging or diverging lens, depending on the different parameters we are going to see. Okay, can you imagine this? I have this glass slab. It acts like a lens. You see, a lens does not have to look like this. Even this can be my lens. Okay, let's see how. Try to figure out the focal length of this combination. Okay, it should not be it should not be difficult. Okay, it's like this. I have this combination here, a plano convex and a plano concave thing. Okay, let's say that this is 1 over f1 is going to be equal to mu1 minus 1. Mu1 for refractive index here, mu2 here. Okay, and then this is 1 over infinity minus 1 over minus r. Okay, so this is 1 over f1. This is actually power p1. Okay, this is power p1. This is 1 over f1 is equal to mu1 minus 1 over r. Okay, are you getting the same answer? Are you doing it the same way? Now here, 1 over, so P2, power of this lens, plano concave lens, 1 over F2, this will be mu2 minus 1, and then here 1 over minus r, okay, minus r, I am using the sign convention, minus 1 over infinity, okay, so this becomes 1 minus mu2 over r. It is going to be negative, okay? So P2 is 1 over F2 is this. Now what is the power of combination? Okay, P is going to be P1 plus P2. Okay, if I simply add it, R is common. If I have add it, minus 1 gets cancelled. I actually have mu1 minus mu2 over R. This is power of this combination. Okay, and what is focal length? Focal length of combination. I can simply write it like this: 1 over P is R over mu1 minus mu2. Now let's look at certain cases here. You see. Okay. So from the outside, if this matching is made perfect, you are never going to like figure out whether it is made up of two different lenses. Everything will appear transparent to you. This boundary is not visible. If it is a perfect match in that case. Okay, do you see? So now this system, it looks like a parallel slab. It looks like a parallel glass slab. Okay, and here let's say that mu1 minus mu2. Mu1 is more than mu2. In that case, power is positive. If mu1 is more than mu2, then power is positive. It is going to have like a converging lens. Okay, so if I have this parallel beam of light on this glass slab, parallel glass slab, they are going to converge here. They are actually going to converge. This is a lens. This actually is a lens. It just looks like this glass slab. It is a glass slab, but it is actually a lens. Okay, so the appearances can be, you see, misleading. Very misleading. Do not run after the appearances. Okay, look at the content. What is the content here? Okay, and then if mu1 is less than mu2, then power is negative. Okay, in that case, the same glass slab with under this condition, okay, it starts behaving like a diverging lens. A diverging lens, okay, like this. Okay, do you see? And now, what if both are same? That also is very interesting. mu1 is mu2, so power is 0. Power has to do with bending. If power is 0, there is no bending. Okay, power has to do with bending. No power, no bending. So that will happen if this is. And anyway, if both become same, then for light there is no change in medium. If there is no change in medium, they pass undivided like this. Here also there will be lateral shift. This is the lateral shift. Okay. This is the lateral shift. Deviation is 0. Power is 0. Okay, by the way, power is also going to be 0. Power is 1 over f is mu minus 1. This is mu. 1 over R1 minus 1 over R2. 1 over f is equal to mu minus 1. 1 over infinity minus 1 over infinity. Parallel glass slab. Both surfaces have infinite radius. Power is going to be 0. Okay, that also you can use. This is one other connection. Okay. Now, so, okay, let's do a few more problems. Few more. Okay. An equiconvex lens of radius 40 centimeter and refractive index 1.5 is kept over a thin glass plate as shown. Okay, so I have this equiconvex lens. Equiconvex meaning thereby both surfaces have same radius. It is kept on this thin glass plate. Okay, it is this thin glass plate. Okay, now interesting thing. Space between plate and lens is filled with water. Okay, filled with water. What is power of combination? So this is space here. The space here is now filled with water. Okay. So now what will be power of combination? Is it going to change or it remains same? If it changes, then what it becomes? Okay. What it becomes? This radius is given. This is r is 40 centimeter. Mu is 1.5, and this here mu is 4/3. 4/3. Look at this problem. And then, let me write one more problem. Two concave lenses, each of focal length 20 centimeter. Two concave lenses, each of two okay, let's write it like this, okay, so I have these two each lenses, each of focal length 20 centimeter, and refractive index 1.5 are kept in contact, and space between them is filled with water. What is power of combination? What is power of combination? Okay, so I have this thing here. Okay. Two concave lenses, they are in contact, and then this space between them is filled with water. What is going to be the power of combination or focal length of combination, whatever? You know one, you know the other. Pause the video, try to figure out. First you do it yourself. Whatever comes to your mind, whatever concept comes to your mind, you do it. Do it yourself. Okay, both problems. Let's see what answer you get. Okay, and then here we are going to discuss it now. If you have not tried it yet, then do not watch. Simply pause the video. Forget about the whole thing, forget about me, and you just solve, focus here, get some answer, whatever comes to your mind, apply that thing. Now I am going to discuss. Let me discuss this. Anyway, both are similar. You know one, you know how to solve the other. This is equivalent to a combination of three lenses in contact. This is a water lens. Equiconcave lens. So if this radius is r, this is r, then this also is going to be r. Do you understand this? This also is going to be r. Here, I have this water lens, a lens made of water. It has some refractive index, I know it already, refractive index of water. 4 by 3. Radius, the radius of this water lens will be same as this. So what we do is, okay, we find their powers P1, P2 and P3. Okay, then resultant will be P1 plus P2 plus P3. Okay, or 1 over F is 1 over F1 plus 1 over F2 plus 1 over F3. Okay. Now I pause here again. Now do your calculation. Okay. Let's solve this first. I'm going to solve this first. Anyway, both we have to solve. If you solve one, you can solve the other. No problem. Okay. Should I solve this one? Let's solve this one. It's not a problem. Here the radius is already given. Okay. 40. Thin glass plate we have to ignore. Okay. So this I can consider like this. Okay. So this is my convex lens. And this is my water lens. Okay. Or water lens. It is equivalent to a convex lens here. Plus this is a water lens. It is made of water. Okay. Now 1.5. This is 40 centimeter here. This is 40 centimeter here. This also will become 40 centimeter. This will become infinite. And this mu is 4 over 3. Okay. Let me come straight to the confusing point. What will be focal length here? P1 is equal to 1 over F1. Okay. Or let me not write P1 because I am going to do it in centimeter. Is equal to 1.5 mu relative minus 1. And then 1 over R1 minus 1 over R2. It's like this here. For the first lens, 1 over F1, this is F1, this is F2, is equal to what will be mu relative? Because this lens is surrounded by air on one side and it is water on the other side. Then what will be mu relative? It is equal to 1.5 over 1 minus 1, 1 over plus 40 minus 1 over minus 40. I should write this, or I should write this 1.5 over 4 over 3 minus 1, and then 1 over plus 40 minus 1 over minus 40. Which one is correct? This is where the confusion happens. Okay. Because if you consider this lens, on one side there is air, on the other side there is water. What should I write? So here there is a very concrete rule, unambiguous rule, unambiguous. You have to make it unambiguous. When you are writing this, you have to calculate power and focal length in air. Okay? P1, P2, P3, F1, F2, F3, all in air. Okay, you don't have to worry about which medium surrounds which side and which surrounds the other side. Okay, so what we are doing is we are separating both lenses. I am keeping both of them in air. I am calculating their focal lengths separately in air, and then I am combining both. Okay, so this will not be correct. Mark this point. It's a very confusing thing. Okay, because of this we make mistakes in the simple problems in exams. So we have to calculate power and focal lengths separately in air, all of them in air, and then I'm combining all of them together. So when I combine all, air is gone. Okay. So now you know how to do this. So now I can do it directly. Okay, you see 1 over f1 is 1.5 over 1 minus 1, like this here. 1 over plus 40 minus 1 over minus 40. Minus 40. Okay. Now, this becomes 0.5 times 2 over 40. Okay. So this f1, it becomes plus 40 centimeter. Understand it, centimeter. This will be plus 0.4 meter. Okay. What will be power? P1. It will be equal to 1 over f. So 1 over 40 and 100 goes up. It becomes plus 2.5 diopter. Plus 2.5 diopter. Now what about f2, the second lens? f2, this is the second lens. Okay. It is 4 over 3 minus 1. 1 over minus 40 minus 1 over infinite, like this. Okay. It is going to be equal to 1 over 3 times this. How much is this? This is like how much? Minus 1 over 40. So minus 1 over 120. So focal length here, f2, it becomes minus 120 centimeter. f2 minus 120 centimeter. Okay. So power minus of 100 over 120. Okay. So minus of 5 over 6 diopter. 5 over 6 diopter. That's it. Okay. 5 over 6 diopter. Now what this is P2. So what is power of combination? Okay. P1 plus P2. Okay. I put both values with sign. So plus 2.5 and plus minus of 5.6 diopter. To solve it, you get the answer. Okay, that's how we do it. So in such type of combination, okay, so this is equivalent to 3 different lenses. So I find their focal length and power separately in air. Then I combine them using this relation. Okay, so I hope that you will be able to solve it on your own. So refractive index, this is 1.5 mu. This mu is 4 over 3. This mu here is 1.5. Powers, radius is not given. Power is not given. Focal length is given. Okay. Focal length here and focal length here is given. Using focal length, I can find radius. Okay. Using focal length, 1 over f is mu minus 1, mu relative minus 1 over r1 minus 1 over r2. It's an equiconcave. So radii are going to be same, r and r. Okay. So it's like this: 1 over minus 20 centimeter focal length minus is equal to, this is 1.5 minus 1 over plus r minus 1 over minus r. No, 1 over minus r. The first surface. If I take this as the first line going from here, first surface negative, second surface positive. It is positive here. Okay. So minus 1 over 20 is 0.5 times minus of 2 over r. Minus 1 over r. What is r? R is 20 centimeter. Now the water lens is going to have same radius. This water lens is going to have same radius. Okay. And this is 4 by 3, the mu value. Okay. What will be focal length? So 4 over 3 minus 1. 1 over plus 20 minus 1 over minus 20. Focal length of the water lens. Okay, understand? This is 1 over 3 times 2 over 20. So this focal length, it becomes plus 30 centimeter. Focal length of water, this water lens made of water lens. Okay. So what is power? Power of the water lens is going to be equal to plus 100 over 30. 10 over 3 diopter. So it is plus 10 by 3 diopter. This is power. Power of what? Power of this water lens only. Now what is this power? So forget about all this. It is not required now. Okay. So power of lens, okay, is 1 over focal length of lens. This is 100 over minus 20. So minus 5 diopter. Okay, for the lens, for this concave lens, for this one lens here. It's like this is my water lens. This is equivalent to okay, what are the powers? This P1 is minus 5 diopter. This P2, this is the power here, plus 10 by 3. Plus 10 by 3 diopter. And this power here, P3, again minus 5 diopter. 20 centimeter minus 5 diopter power. What is power of combination? P1 plus P2 plus P3. 5 minus 10 over 3 plus 5. Plus 20 over 3 diopter. Plus 20 over 3 diopter. This is power of combination. So this combination will behave like a converging lens. Okay. This combination is going to behave like a converging lens. Oh no, not converging. This is minus here. It is plus here. This is minus, here plus, here is minus. Okay. So minus 30 plus 10, minus 20. Okay, it is going to be minus here. It is going to behave like a diverging lens. Okay, so if I have this incident rays falling on this system, they are going to be diverged like this. Okay, the combination behaves as a diverging lens. Of what power? This is the power. What will be focal length? Focal length will be 1 over P. So minus of 3 over 20. Now this will be meter. This will be meter. Okay. This will become minus 15 centimeter. Minus 15 centimeter. Okay. So that's it for this lecture. We conclude this lecture and this chapter also. Okay. Do the problems. Okay. Do not give up the problems. Try at least 3-4 times before giving up and before going for discussion and looking for the answers and solutions and all that. Okay. At least 3, 4, 5 times you must try a problem before calling it quits. Okay.